Next, let's take a look at the very high level application architecture for a production app. You may or may not already be familiar with a lot of these concepts, but I think this will serve as a really good template for us to expand upon for the rest of this course. Throughout the course, we'll be digging in deeper into a lot of the concepts I'm about to introduce right now, but I think it's really useful to take a step back and focus on what exactly we're trying to achieve here in the first place. So we're going to start this from the perspective of a developer. So this will be pretty relatable for us. We know that as developers, we write code, which has to get deployed somewhere. And we know that eventually our code has to reach some server where our code is actually going to run on. Now, you may already be familiar with what a server is, but for now, let's assume that it is just a computer that can handle requests, meaning that it can serve users. We'll expand upon that in a bit and go even further later on in the course. And usually there's kind of an intermediate step before our code can reach a server. The code has to be built and deployed. That could happen on the dev's local machine. More commonly, it can happen on some type of CI/CD server, continuous integration, continuous deployment. This is a lot more common in the professional world for production grade applications, but it's sort of an optional step here. Now, our server is also going to need to store some data, so we could have some type of external storage mechanism, which really could be anything. It's really open-ended. Your first thought might be that this is a database, and yes, that's one valid possibility, but there's also many other ways we can store information and data. So this is our persistent storage. Now, of course, our server, if it's a computer, it may also have some type of storage mechanism. It could have its own disk, but we know that that has its own limitations. So this is a distributed storage mechanism. So this could actually be running on its own computer. So we assume that this storage is not running on the same server. It's connected over a network. These could even be located in different parts of the world. Now let's take this from an external user's perspective. If they want to use our application code running on our server, they have to communicate with that server. So they can maybe send a request, most likely from their browser. So if we're serving some front-end code from here, our server would respond with the JavaScript HTML code that the user needs on their browser to load our page. Our server could also be some kind of back-end server where from the browser, the user is making a request to our API, and then our API responds with, some type of data, maybe in the form of JSON, which is a popular data format that you may or not be familiar with. But what if we have a lot of users and they're all making requests to our server at the same time, and our single computer here can't handle all of the requests on its own? Well, we could first determine the bottleneck with our server. Maybe our CPU is what's slowing us down here. Maybe it's just not fast enough, and then we can get a better CPU for our server, and then our server will be able to handle more requests. Maybe it's a limitation with our RAM. Maybe by getting more RAM, our server will be able to do more with it. It could be some hardware limitation with the single server. So from what we learned about computer architecture, we could just take a single server and make it better. We could upgrade its CPU, its RAM, its disk. We could upgrade the computer itself. This is an example of vertical scaling. To take a single resource like a server, like our computer over here, and then making it better. You can think of it as like adding a block to that server. We're making that single server better. And this is pretty simple conceptually. For us to make our system better to handle more traffic, we vertically scale it by getting a better server here. But as we learned earlier, computers have limitations. No matter how fast our CPU is, it has a limitation. It won't be able to handle infinite requests. So to make our system even better, we can use a different technique, which is called horizontal scaling. Horizontal scaling is to actually take our server and make more copies of it. So we won't just have one server that's running our code. We'll actually have multiple servers running our code. The benefit of this is that if we have more users, all of the users don't have to talk to a single server. They can actually talk to one of the other servers. This way, we'll be able to handle more requests at the same time. You can sort of see why this is called horizontal autoscaling, because we're not actually making any of these individual servers better. We're just introducing more of them to handle the same task. Now, the problem we introduce when we have multiple servers handling requests is that when a user makes a request, how do we know which server that request should go to? Well, that's where the load balancer comes in, and we won't go super in depth right now, but let's assume that the load balancer will be able to handle that for us. It'll basically forward the request to the server that has the minimal amount of traffic so that each of the servers has a balanced amount of traffic. We don't want one of the servers to be handling all of the requests and then maybe another server isn't really doing anything. That wouldn't be very helpful. In that case, what would even be the point of horizontally scaling? So this is obviously a simplified diagram, but let's assume we have multiple servers and the load balancer is balancing the requests among those servers. Now, our servers don't have to run in isolation. Our servers might actually be communicating with other servers as well. For example, my code for neetcode.io is communicating with other APIs, for example, the Stripe API to handle payments. And of course, we could have many such external servers that we're communicating with, and I have it shown simplified here. Now, from a user perspective, this is pretty much all that's going on for our application, but we know that as developers, we have a few more responsibilities to handle. The same way when we run code locally, we sometimes have logging or print statements so that we know what's going on within our code, whether our code is working properly or that there are some issues going on. For us to get some insight into how our server is running, because it's not running on our local machine, we also use log statements, but we might not be able to store all of those on our server. In fact, we don't need to store them all on our server because our server isn't really going to be interacting with them. We as developers are going to be interacting with the log. So we will have possibly some external service, and that external service is going to store our logs for us. So every time a user makes a request, whether it goes good or goes bad, our server is going to log that information into that external service, which is going to handle all the logging for us. Now, the user will never have to directly interact with this, but us as developers, if we want to know how did the user's request go, is our server having problems, what were those problems, we as developers will interact with that logging service. Now, logs don't tell us the entire story. What if one of our servers isn't running very well? Maybe it has a faulty CPU or something like that, and we want to know about the resources that our server is using. Is the CPU being taken up? Is the RAM being taken up? Maybe the storage is already full. Maybe some type of issue is happening with our server. To get that insight, we would have a metrics service, and this would provide us all of the metrics that we care about of how our server is running. Is it responding to all requests? Are some requests failing? Are the resources of our server being taken up? Basically, any type of application metrics or resource metrics that we would need about how our application is running. Now, some of the metrics might directly come from logs. These would be log-based metrics. We could, for example, log something every time that a user gets a successful request, and we could log every time a user gets a failed request, or failed response rather. And we could use these logs to create metrics, and metrics are usually displayed in terms of time series charts. Like, we want to know, how was our CPU going over time? Like, was it positive trend or was it a negative trend? What was going on? And that's why log-based metrics can also be used, because logs are naturally time series data. Every time we log something within our server, it has some type of timestamp associated with it. Now, as developers, we can look at the metrics and get insight into how the application is running. But if something goes wrong, you wouldn't want to have to manually go and look at the metrics to realize what's going on. Or even worse, a user would tell us, like email us, that something went wrong with our application, because users are constantly using the app and they would be the first to know if something went wrong. We don't want this to happen. We want, as developers, to know immediately when something goes wrong. So we want a push notification from the metrics. To accomplish this, we have our metrics feed data data into an alerting service, which will, for example, tell us when a metric has reached some threshold. So for example, let's say usually 100% of user requests get a successful response. But what if that threshold dips below 95%? We could set up our alerting service such that when that particular metric goes from 100% to 95% or below, our alerting service will actually automatically notify us. You can see this chart is obviously getting large, even though it's quite simplified. We can see how complicated an application can be. Our alerting service will notify us developers immediately as that metric dips below some threshold, and we will be notified probably at the same time as some users, but this is about as quickly as we could be notified. As soon as that happens, of course, unless we can predict the future, we won't know in advance. So these are kind of the key components of an application from a developer's perspective, and things can get a lot more complicated than this. And that's what we'll be covering throughout the rest of this course. And there's a lot of things beyond this that we haven't really talked about yet, especially when it comes to networking, which is how all of these components can even communicate with each other in the first place, because they're not necessarily on the same computer. So if these components are running in different computers, there's going to be some network component between them, and networks can get pretty complicated. As developers, we don't have to know all the details, but at least understanding the basics is going to be really useful when it comes to designing these large-scale applications.